So the next part of the chapter is chemical equations and calculations. Chemical equations and calculations, or sometimes you can also take chemical reactions. Chemical reactions cut. So here I repeat, the chapter deals with chemical equations and calculations and chemical reactions. Here the fundamental terminology involved is, that is, a chemical change, then chemical equation, chemical change and a chemical equation. This chemical change and chemical equation, what do you mean by chemical change? The process which is physical. Okay, when you say chemical change, if you take not physical, you can take the process which involves conversion of reactants, conversion of one substance, conversion of reactants, or else you can just put it in like this: conversion of reactants to products. Conversion of reactants to products is simply a chemical change, and this conversion of reactants to products actually involve because of a chemical reaction. Because of chemical reaction, it involves the conversion of reactants to products because of chemical reaction. So a chemical reaction involves a chemical equation. When you say a chemical equation is made up of of course we have reactants separated by products. Reactants separated by products. So if you take a chemical equation, so therefore if you go for a chemical equation, reactants and products are separated by the arrow. We have a right side arrow and we have a tail. This we call it as tail, and this we call it as the head. Head is faced by products and tail is faced by reactants. So what is happening here is this: what is the information? A chemical equation involves the two components. A chemical equation is given by two components, reactants and products. A chemical equation is given by two components, reactants and products, separated by an arrow. An arrow is made up of head and tail. And what information we can gather, that is from the chemical equation during the chemical reaction in the form of chemical equation, what information we can gather? We can gather all the information from the chemical equation from reactants to products. That is, this chemical equation is basically based on the type of chemical reaction. Based on the type of chemical reaction, we can take here, that is A. Suppose if you are simply taking chemical combination, say I am taking chemical combination, what information you can gather from chemical combination? Suppose for example you take carbon solid reacts with O2 gas, gives rise to carbon dioxide gas. That means one element and one molecule. Carbon is a solid, oxygen is a gas and carbon dioxide is a molecule again. That means what information you can gather? 1 mole of carbon solid, 1 mole of carbon solid reacts with 1 mole of O2 gas, 1 mole of O2 gas giving rise to 1 mole of carbon dioxide gas. This is the information which you can gather from the chemical combination. Suppose you are taking chemical decomposition. Chemical decomposition. If you are taking chemical decomposition, and mind you here carbon solid and oxygen gas, these two are reactants, and carbon dioxide is a product. It's a product. So similarly in the chemical decomposition, suppose I am taking CaCO3 solid, limestone, calcium carbonate. Upon heating, you heat it, you get carbon dioxide gas plus calcium oxide solid. That means here calcium carbonate is a reactant and carbon dioxide and calcium oxide are products. Reactants and products are separated by the arrow, wherein which calcium carbonate is a solid and carbon dioxide and calcium oxide. Carbon dioxide is a gas molecule and calcium oxide is a solid molecule. And here calcium carbonate is reactant and carbon dioxide and calcium oxide are products. So in this way we can gather the information from the given chemical reaction as long as the chemical process is continued. So the next type of chemical equation you can take, we have studied about in the previous chart, we have studied about the chemical combination, we have studied the chemical decomposition. Sometimes you can even go for chemical displacement. Chemical displacement. If you go for chemical displacement, suppose for example you are taking zinc is a solid and it reacts with H2SO4 liquid, it gives rise to zinc sulphate liquid plus H2 gas. So what you are noticing here is this sulfuric acid, this is acid and this is metal. Metal is coming and replacing the hydrogen gas, H2 gas, okay, from the acid. So you are getting zinc sulphate as a salt and this is a gas. This is a sort of chemical displacement. So what information you can gather from this? This is a chemical displacement. Here solid is reacting with liquid, solid reacts with liquid, liquid is acid, solid is metal, giving rise to, again it gives solid plus a gas is obtained. This is the information we can gather from chemical displacement. Sometimes we can take combustion reaction. Combustion reaction. If you go for combustion reaction, suppose I am taking CH4 gas plus oxygen gas gives rise to carbon dioxide gas plus H2O liquid plus energy. Because all combustion reactions are exothermic in nature, they release energy. So balance the equation, we can take 2 molecules here, 2, we can take 2 here, that means from the equation this is 1 and this is 1. So here 1, 2, 1 and again 2 in chemical equation are called molar coefficients. So if you want to balance the equation, if you want to balance the given equation, you have to adjust the balancing of equation through molar coefficients. You can balance the equation only through the adjustments of molar coefficients. That means you can take 1 mole of methane, that is methane reacts with oxygen to form carbon dioxide and water. So after formation of carbon dioxide and water, you have to check how many number of oxygens are present and how many number of hydrogens are present. If you take oxygens, we have only 2 oxygens, so that's why to see that the number of oxygens are same in the reactants and products, we are multiplying that 1 mole of oxygen molecule with 2. And similarly here also, because we have 4 hydrogens in methane, we are taking 2, multiplying the water molecule with 2 as a molar coefficient. So 2 2s are 4 hydrogens. Here also 4 hydrogens. Here we have 2 oxygens plus 2 oxygens, 4 oxygens, and here also we have 2 2s are 4 oxygens and 1 carbon and 1 carbon. So the entire reaction has been balanced. So that means from a given chemical reaction or a chemical equation, we can gather the information about the molar coefficients, we can gather the information about the physical states of reacting atoms or molecules. These reacting atoms or molecules can be reactants or they can be products. This is the information we can gather. So like this, you can take as many number of examples. One more last example I am going to give, that is you can take sometimes you can take double displacement reaction also. You can take, if you take double displacement reaction, silver nitrate when it reacts with the barium chloride, you find that you get silver chloride plus barium nitrate. That means what is happening here, the chloride ion is being replaced by the nitrate group and the chloro group is replaced by the nitrate group. The chloro group is occupying the nitrate group and the nitrate group is occupying the chloro group. That's why here we are getting silver chloride. Okay, silver chloride as a precipitate and barium nitrate solution. This is aqueous, this is also aqueous, this is also aqueous, this is precipitate, so white precipitate. So in this way we can study the different types of chemical reactions and we can gather the different types of information from the chemical reaction or in the form of chemical equation. So the next part of the discussion is rate of chemical reactions. The word rate here we mean the speed or the velocity with which the reaction gets completed. Take these examples, random examples I am going to give you. Digestion of food, rusting of iron, then standardization of oxalic acid, reaction of metal with the dilute acid, reaction of metal with the concentrated acid. fermentation process. What you are noticing in all these cases, fermentation process, it's a slow process. Metal reacts with constant acid very fast. Metals reacts with dilute acids very slow, or you can say slow reactions. You can say slow. Standardization of oxalic acid, moderate reactions. Moderate reactions. Rusting of iron and digestion of food, very slow reactions. Slow reactions. If you take digestion of food, in particular, if you are taking digestion of food, whatever the food we consume, that food is in the form of complex carbohydrates. These carbohydrates with the various enzymes which are present in a body, they are broken down into the simpler substances in the form of proteins and amino acids, and these proteins and amino acids, they are absorbed into our body. For this absorption to take place in our body, it requires an amount of metabolism and catabolism, and it's a time consuming process. That's the reason the digestion of food which we take, it takes a lot of time, minimum 2 or 3 hours of time, because that's how the metabolism and the catabolism works in our body. That's why we can say the digestion of food is absolutely a very slow process. If you go for rusting of iron, yes, rusting of iron also is a very slow process, because when the water which is coming in contact with the surface of a metal, rusting of iron means iron is a metal, iron has a lot of affinity towards the water, and if water contains any dissolved salts in it, these salts also, they try to form a layer on the surface of the metal, and slowly chemical interaction takes place between the iron and the other metals which are present in water, and as a result of that, you find that the color of the iron slowly starts changing. It becomes the reddish brown color, sometimes because of rusting, or sometimes it becomes a pale green color. All these color changes on the surface of iron can be indicated by the rusting of iron. Standardization of oxalic acid is something like, it's a typical reaction. You know the formula of oxalic acid, H2C2O4 plus H2SO4 plus KMnO4. For example, if you take, we can take here K2SO4 plus MnSO4 plus carbon dioxide plus water. Carbon dioxide plus water. If you take, I think if you are taking 5 here, then here I am taking 10, and here if I am taking 2 over here, then I am going to take 2 over here. Already number of sulfates, you can see number of hydrogens. If you take 5 to 10, number of sulfates we have 3, so I think if I take 3 over here, sulfates are already balanced. So here number of hydrogens 10, and plus 5 to 10 and 3 to 6, 16 oxygens. So I think if I am going to take 8 hydrogens there as molar coefficients, 5, 3, 2, 2, 10 and 8, I think maybe the reaction is already balanced, because we have 2 potassiums and 2 potassiums, we have 2 manganese and 2 manganese, we have 3 sulfates, 1 sulfate here and another 2 into sulfate, 3 sulfates are balanced. There are 2 carbons, there are 10 carbons, you can take 10 carbons, you have 16 hydrogens, 16 hydrogens are balanced, 5 4s are 20 oxygens, 5 4s are 20, and 20 plus 4, 2 4s are 8 oxygens, 28 oxygens. So this is 20, 10 2s are 20 oxygens and another 8 oxygens, so the entire reaction is getting balanced. So here what is happening here is, you take 20 ml, this is oxalic acid, H2C2O4 is the oxalic acid, and this is sulfuric acid, and this is potassium permanganate, potassium permanganate, and this is manganese, manganese sulphate. So this reaction to take place, so here this we take 20 ml and this also we take 20 ml, and both this 20 plus 20, it is this 20 ml and 20 ml, we just titrate with K-4 and that will result in the formation of manganese sulphate, and it will take half an hour or 45 minutes of time. The temperature operates at around 80 degrees centigrade. So this is a perfect example. This is a perfect example of moderate reactions. And reaction of metal with dilute acids, this is not a new reaction. I think I can just show you here. And if you take very simple example, I am going to give you. Suppose zinc, if it is zinc solid, if it is reacting with HCl, which is dilute, immediately you can find that, of course, you get zinc chloride. Zinc chloride you are going to get aqueous plus H2 gas is liberated. The evolution of hydrogen gas is very slow. That's because the acid is dilute. But the same reaction if you carry out with the, say, zinc solid, if you're carrying it out with the HCl concentrated, then you find that immediately C1C conc concentrated. Yes, here you are going to get zinc chloride, no doubt about it. Zinc chloride you are going to get. The thing is here evolution, of course, aqueous zinc chloride salt is evolved plus H2 gas, because the acid is concentrated. The reaction becomes very fast. Here the acid is dilute, that's why the reaction becomes very slow. In this way, we can simply differentiate between the very slow reaction, we can simply differentiate between very slow reaction or fast reaction. Sometimes you can say simply slow and fast reaction. No need of using very, just you can say slow reaction and fast reactions. So today we would like to understand this topic in a very simple manner by selecting some random examples. Say for example, I am just giving you some examples like iron solid plus H2O liquid gives rise to Fe2O3 solid plus H2 gas. Say, how do you balance this equation? That is, I am underlining here. Here also I am underlining. Here also I am underlining. So what we can do here is, like here we can see that the number of hydrogens are 2, and here the number of hydrogens are 2, and here the number of hydrogens are 2, number of oxygens are 3. Here we have only one oxygen. So the first thing what I am going to do is, I am going to mark 3. I am going to place a molar coefficient 3 besides water. This 3 is not only balancing the number of oxygens, it is also balancing the number of hydrogens. So here by marking 3 as a molar coefficient beside water, you are increasing the number of hydrogens from 2 to 6, but here we have only 2 hydrogens, so mark 3 here as a molar coefficient. So what you are noticing here, that means as of now the number of hydrogens are balanced, 3 to the 6 hydrogens and 3 to the 6 hydrogens, 3 oxygens and 3 oxygens. We have 2 irons, but we have only 1 iron, so therefore this is how the irons are getting balanced and the entire reaction is getting balanced. Take one more example, that is this is the first one. Go for second one. Suppose I am taking C6H6 benzene, that is liquid, plus oxygen gas gives rise to that is carbon dioxide gas plus water liquid. So here what I can do is, just as how we have done in the earlier cases, I am marking here as one unknown molar coefficient, unknown molar coefficient, unknown molar coefficient and unknown molar coefficient. In the above reaction for irons already they are balanced, so 1 we place it here, that the reaction is going to get balanced, no problem, that's already balanced. Now if you go to the second part of the reaction, that is here, you are finding that there are in benzene, of course this is benzene, in this benzene we have 6 carbons, here we have only 1 carbon. Because there are 6 carbons, I am going to place the molar coefficient 6 besides carbon dioxide. Thereby here you are finding that the number of hydrogens are 6, but here we have only 2 hydrogens, so that's why mark 3 here. The number of hydrogens are balanced, and here you have 3 oxygens, and here we have 6 to 12 oxygens. 6 to 12 oxygens plus 3 oxygens. Total 15 oxygens are there, and here we have 2 oxygens. Either you can take 7.5 moles, or the 7.5 you can write it as 15 by 2. If you multiply the oxygen with 15 by 2 moles, then this 15 by 2 is nothing but 7.5. 7.5 into 2 is again nothing but 15 oxygens. So therefore here you are finding that the number of carbons are balanced. Number of carbons 6 carbons, number of hydrogens 6 hydrogens, 6 to 12 plus 3 15 oxygens. Oxygens are balanced, everything is balanced. So 1 mole of benzene, so mark it here as 1. The reaction is going to get balanced. This is one kind of a reaction where you can easily understand how the chemical reaction is getting balanced. Look at this, go for the next part of the reaction. Suppose sometimes a situation arises like this. Ammonia gas plus chlorine. This is ammonia is in excess. It gives ammonium chloride solid plus nitrogen gas. What if you are taking, how to balance the equation? So to express the molar coefficient, mark here 1 molar coefficient, mark here 1 molar coefficient, here you mark a molar coefficient, and here also you mark a molar coefficient. So what you are noticing here is, suppose because already here 1 nitrogen and 1 nitrogen, 1 nitrogen, 1 nitrogen, 3 hydrogens, 4 hydrogens. We have 2 chlorines, 1 chlorine. We have total number of nitrogens 3 are there. 4 is the even number. 4 hydrogens are the even number because already nitrogens are 3. So there is no use of placing 4 here. 4 means I am doubling the 4 with 8. Suppose if I am taking 8 moles of ammonia, say for example, hit and trial. If there is no concept involved in the balancing of complex reactions, you have to use hit and trial, that is guess method. The guess should be so quick that you have to check the number of hydrogens on the product side and number of nitrogens on the product side. Number of hydrogens are 4 is even, number of nitrogens are 3 is odd, but 4, if you mark it as 4, you could not be balancing either nitrogens or hydrogens. That's why better you go for higher even number. The higher even number is 8. If it is 8, then you have 8 nitrogens and 24 hydrogens. 8 nitrogens and 24 hydrogens. So 8 nitrogens means what I'm going to do here is, I think I can take over here, because 24 hydrogens means you have 4, so I am marking here 6. By marking 6, you are not only balancing the number of hydrogens, you are not only balancing the number of hydrogens, you are also balancing the number of nitrogens. Only thing is that you have to balance the number of chlorines, so mark it here as 3. This is one way of balancing the chemical equation. So this is one of the typical examples. So likewise, one more last example I would like to give you. Suppose for example you are taking say for example you are taking zinc solid, reacts with H2SO4 aqueous concentrated, giving rise to zinc sulphate aqueous plus sulfur dioxide gas plus H2O liquid. So you have to balance this equation. If you want to balance this equation, underline the molar coefficient, underline the molar coefficient, underline the molar coefficient, molar coefficient and molar coefficient. So what we can do here is, like we have 2 sulfurs are there. First thing is I am guessing with 2 sulfurs. Suppose if I am taking 2 over here, by chance if I am taking 2 over here, the number of oxygens are 8. We have 2 sulfurs and number of hydrogens are 4. So blindly, suppose if I am going to place 2 here, yes, number of hydrogens are balanced, 2 2s are 4 hydrogens are balanced, then 2 sulfurs are already balanced, then we have 2 4s are 8 oxygens, yes, 4 oxygens plus 4 oxygens plus 2 oxygens plus 2 oxygens, yes, 8 oxygens balanced and 1 zinc solid is balanced. So therefore I am going to mark it as 1 as a molar coefficient. So we can easily balance the given chemical equations or chemical reactions by using little bit of common sense, little bit of awareness in the reaction, little bit of awareness of different groups which are involved in the chemical reaction. Little bit of practice can make you to balance any type of given chemical equation in your own terms. As of such, when you are balancing the chemical equation, there's no need for us to use any particular method. It's better always use the hit and trial method, and always maintain the time management when you are trying to balance the given chemical equation. So here, because it is zinc is only 1 mole, 1 zinc atom is there, so here I am going to take 1, so the entire reaction is balanced. So the next part of the discussion is, that is energy changes. Energy changes taking place in a given chemical reactions. So when you say energy changes, here energy changes of energy changes are made up of you can say thermal decompositions is one type of energy change. Thermal decomposition is one type of energy changes. Then that is exothermic changes, exothermic reactions, endothermic reactions, endothermic reactions. These are the 3 reactions where we can utilize and we can discuss. So here, if you take, for example, if you are taking thermal decomposition, take CaCO3 solid, this is limestone. Upon heating, you heat it, it gives calcium oxide plus carbon dioxide gas. Mind you, this is limestone, and this is quicklime. Limestone and quicklime. So that means you are supplying heat here. That means the limestone in the form of calcium carbonate, it is getting decomposed to give one single compound. Upon heating, it is able to give 2 products. One product is calcium oxide, otherwise we call it as quicklime, and also the carbon dioxide gas is evolved. This is one type of thermal decomposition. Also, you can take one more example, that is ammonium nitrate is a solid. Upon heating, you heat it, so applying the heat, so you get N2O gas plus H2O liquid. N2O gas is nitrous oxide, otherwise also called laughing gas. And this is solid. Ammonium nitrate is solid. Likewise, you can take plenty of examples. You can take lead nitrate is a solid. You heat it. If you heat, you get lead monoxide, which is a solid, nitrogen dioxide, which is a gas, and also a small amount of oxygen gas is also evolved. This is thermal decomposition. So balance the equation. If you want to balance the equation, I suppose already we have, suppose if I am taking 2 over here, there is no use. So suppose if I am starting over here with 2, if I am placing this as a molar coefficient as 2, and lead nitrate, there are 2 leads, so I am just placing 2 as a molar coefficient besides lead oxide, that is plumbous oxide. This is plumbous oxide or lead monoxide. There are 2 nitrogens, so take 2 over here. Number of oxygens, 3 2s are 6, 6 2s 12. So already we have 2 2s 4 oxygens plus 2 oxygens 6 oxygens. Then I think if I am going to place 3 over here, then the entire number of oxygens are going to get balanced. That is, you can see here, that is 2 moles of lead nitrate upon heating gives 2 moles of lead monoxide, 2 moles of nitrogen dioxide and 3 moles of oxygen. So these three are the best examples of how the thermal decomposition takes place. So this comes under thermal decomposition. Thermal decomposition. First example, second example and third example. So this is lead nitrate. This is the third example, lead nitrate. So the next part of the discussion in thermal decomposition is second category, in thermal decomposition, B, in thermal decomposition. In thermal decomposition, one more category, that is the best example in this is electrolytic decomposition. Electrolytic decomposition. If you go for electrolytic decomposition, what do you mean by this electrolytic decomposition? This means that you are subjecting electrolysis, in other words, electrolysis of acidulated water, electrolysis of acidulated water using inert electrodes. That's because why we say acidulated water, pure water is a bad electrolytic conductor. Pure water is a bad electrolytic conductor. So to improve its conducting nature, we need to add small amount of acid. So water, when it is mixed with water, liquid, when it is mixed with H2SO4 in small amounts, this turns to acidulated water. Good electrolytic conductor. Good electrolytic conductor. So what is happening here? I am just drawing one small diagram here just for understanding purpose. What I am doing here is I am just taking one small electrolytic vessel and I am just releasing two inert electrodes through the platinum wires and the platinum plates, and we are connecting it to the conducting external circuit. This is the power source, battery, and one will act as anode, A for anode and B for cathode, C for cathode, A for anode, and this is cathode electrode, and here in this we are going to fill the electrolytic solution. H2O, that is acidulated H2O. You find that what is the reaction mechanism taking place during the electrolysis, and this is nothing but electrolysis taking place. So what is happening here is, take the reaction mechanism at anode. At anode we can take, that is 2 molecules of H2O liquid gives rise to 4 H plus ions plus oxygen gas plus 4 electrons. De-electronation takes place. This is oxidation. At cathode, that is H2O, 4 molecules of H2O liquid plus 4 electrons gives you, that is 4 OH minus ions plus 2 moles of H2 gas is evolved. So this is first equation and this is second equation. So when you add both these equations, you are going to get this 4 electrons and 4 electrons, they get cancelled. This is reduction, and here 4 plus 2, 6 water molecules in the liquid state, they give 4 H plus ions plus 4 OH minus ions plus O2 gas plus 2H2 gas. Or you can write the same reaction as, or because we have 4H plus ions and 4H2O, this 4H plus ions and 4H2O can be written as this 4H plus ions and 4H2O. I'll just write this as this equation. This I'll write it as 6H2O minus 4H2O gives rise to O2 gas plus 2 moles of H2 gas. This also means that this 4H2O, 6H2O minus 4H2O, ultimately it will result in, that is 2H2O liquid, 2H2O liquid gives rise to 2H2 gas plus O2 gas. So this completes the electrolytic process of water. This completes the electrolytic decomposition of water. This completes the electrolytic decomposition of water. So here I am just marking all the separations very clearly with a positive sign, no confusion. It's a very important reaction wherein which finally we are getting the thermally decomposed, electrolytically decomposed water molecules. They are giving 2 moles of hydrogen gas and 1 mole of oxygen gas, and these are the anodic reactions and these are the cathodic reactions, and this is the net equation which you have to understand. So the next part of the discussion here is, that is photochemical decomposition. Photochemical decomposition. If you go for photochemical decomposition, here catalyst, reactants gets converted to products in the presence of sunlight. The sunlight, mathematically we give it in the form of h mu. H mu is nothing but the frequency of radiation. H is the Planck's constant and mu is the frequency of radiation, and we can just call this as a photochemical reaction. This is photochemical reaction. This is a photochemical reaction. Take some examples of photochemical reaction. One is, the best example is, we can take the decomposition of hydrogen iodide gas in the presence of sunlight, that is H mu. Sunlight acting as a catalyst, it gives H2 gas plus I2 gas. That means 2 moles of hydrogen iodide gas is decomposing to give hydrogen gas plus I2 gas. Sometimes you can also take ammonia gas, 2 moles of ammonia gas in the presence of sunlight, that is H mu. It gives 1 mole of nitrogen gas plus 3 moles of hydrogen gas. All these comes under the photochemical reactions. We call them as photochemical reactions. Photochemical reactions or photochemical decomposition, because here the sunlight is acting as a catalyst. Sunlight is mathematically given by H mu, where H is the Planck's constant and mu is the frequency of. So the next part of the discussion here is, that is displacement reactions. If you go for displacement reactions, if you go for displacement reactions, that is it's like this principle. If you go for principle, more reactive metals displaces less reactive metals from its salt solutions. So for example, if you take the reactivity series, if you take the reactivity series of metals, you find that if you take copper if you take, and zinc if you take, and lead if you take, we can see that copper and lead are more reactive, and zinc and lead are more reactive, and copper is less reactive. So if it is less reactive, then you can take one equation, zinc solid plus copper sulphate aqueous, which is bluish color solution. It immediately, here zinc oxidation number is 0, in copper sulphate copper oxidation number is +2. So this copper is getting reduced. Zinc is acting as a reducing agent. If it is acting as a reducing agent, then copper sulphate, it gets converted to copper solid plus zinc sulphate aqueous. This is, you can say that blue color fades. In the case of copper solid, blue color fades, and the zinc sulphate is going to become white precipitate. So here this is one type of reaction where that means zinc is reducing the copper sulphate to copper, and by itself it is getting oxidized. In zinc sulphate, zinc is +2 and copper is 0. This is one type of reaction. Then you can go for one more reaction if you want. That is likewise, if you take iron, if you take iron solid and if you treat it with copper sulphate, here iron solid, when it reacts with copper sulphate aqueous solution, this iron gets converted to ferrous sulphate, and copper is getting reduced to copper solid, and here you find that iron is going to become brownish colored. It appears a brownish color solution. This is bluish color, and this color fades here. Less bluish color is obtained because it's a solid. From this equation, it's very clear that between iron and copper, you can see that iron is more reactive. Similarly, between zinc and copper, that is, zinc is more reactive. So the next part of the discussion is double displacement reactions. Double displacement reactions. If you take here, when two or more atoms or groups of a compound react, exchange of radicals means cations or anions. Cations or anions occur, resulting in formation of a new salt and a precipitate. PPT stands for a new salt, PPT stands for a precipitate, PPT stands for precipitate, and a new salt is formed. Suppose, for example, we take sodium sulphate aqueous plus barium chloride aqueous, it gives barium sulphate in the downward arrow plus sodium chloride aqueous. So what you are noticing here is this is a precipitate. It's a white precipitate. It's a white precipitate. So for example, what are the ions involved here? For example, sodium sulphate contains Na plus and SO4 2-, and barium chloride contains one barium ion and one chloride ion. So there is an exchange of radical is taking place. Exchange of radical is taking place. The sulphate ion, which is anion, is going towards barium, and the chloride ion, which is anion, is coming towards sodium cation. So therefore it is resulting in the formation of, this results in the formation of, one is sodium chloride comma barium sulphate. This is called double displacement reaction with exchange reaction. This is example 1. Now example 2, suppose for example example 2, if you take, that is silver nitrate reacts with the barium chloride aqueous. Again aqueous, we get here AgCl precipitate, white precipitate plus barium nitrate aqueous. So what are the ions taking place here? In silver nitrate we have one Ag plus ion and one nitrate ion, and in barium chloride we have one barium ion plus one chloride ion. So exchange of ions are taking place here. So barium is being exchanged towards nitrate, and silver ion is getting exchanged to chloride ion. So this is the kind of exchange taking place, and therefore you find that here we get two compounds. One is silver chloride, another one is barium nitrate. Silver chloride and barium nitrate, exchange of ions are taking place. So in this way we can study about the displacement reactions, wherein which the exchange of radicals are taking place between the reactant molecules, such that one precipitate and one new salt is formed. So here this is the precipitate and this is a salt, soluble salt. Again this is soluble salt, insoluble precipitate. Wherever we are calling it as precipitate, it is insoluble. Wherever it is soluble, that means that salt is completely soluble in, it is able to dissolve itself in water. So if you go to the same displacement reaction, one more last example let us take. That is, I am taking here, that is the same displacement reaction, example 3 of displacement that is double displacement reaction, that is lead nitrate aqueous plus potassium iodide aqueous gives rise to PbI2 precipitate we get, plus PbI2 precipitate we get, and potassium nitrate 2 moles aqueous, which is soluble salt. So it is very clearly understood that, of course we need to balance the equation. It's very clearly understood that the lead iodide is forming a insoluble precipitate. It is going to form insoluble precipitate. So here when you go to the precipitate, it forms a color. It can give the white precipitate, insoluble white precipitate. And here it is very clearly understood that these are some of the most prominent examples of the double displacement reactions. Here also, in the case of lead nitrate also, we can have one plumbous ion, we have one nitrate ion, and here we have one K plus ion, and here we have one iodide ion. So here the iodide is getting exchanged to plumbous ion and the nitrate is getting exchanged to K plus ion. So this comes for the double displacement reaction. Next, after this we will go for the next topic, that is we can go for that is redox reactions. redox reactions. In redox reactions, what is the meaning of redox reaction? Red ox. In this only meaning is there. We cut the word into two halves. That is redox reaction, a chemical equation involving both oxidation and reduction. A redox reaction which involves both oxidation as well as reduction is redox reaction. So reduction involves gain of electrons, addition of hydrogen, and sometimes there is a decrease, gain of electrons. It involves gain of electrons, addition of hydrogen. This, therefore, the reduction sometimes it's also called electronation. It's also called electronation. Go for oxidation. Oxidation, loss of electrons, addition of oxygen, also called de-electronation. So here if you take, suppose for example, if you are taking reduction and oxidation, a reaction can involve both oxidation as well as reduction. For example, I can take some reactions, for example, okay, so we will study the reactions between reduction and oxidation. So here if you take the equation that is cupric oxide when treated with hydrogen. Cupric oxide is a solid, hydrogen is a gas. When treated with hydrogen gas, it forms Cu solid, copper solid plus H2O liquid. So what you are noticing here this hydrogen, we are trying to add hydrogen. H2 is added. And oxygen is removed. H2 is added and oxygen is removed. Because oxygen is removed and H2 is added. When you add H2, when you are adding H2, it means that this is reduction. You can take this as reduction, and here oxygen is being removed. When oxygen is being removed, you find that this is also reduction. That's because removal of oxygen is reduction, addition of hydrogen is also reduction. So therefore, in a nutshell, I can just explain again, once again I can give you the explanation. Cu plus H2 gives rise to Cu solid plus H2O liquid. So here hydrogen is acting as a reducing agent. Copper oxidation state is +2. Hydrogen oxidation state is 0. Again copper oxidation state is 0 and oxygen oxidation number is -2. So if you take the hydrogen, if you are taking hydrogen here 0 to, this is from +2 to, you can take it like this. What we can do is, I will show it like this to make it to better understand. Take the oxygen and take copper. So from oxygen, here in cupric oxide, oxygen is -2 oxidation number, and here oxygen is -2, so there is no change in the oxidation number. But if you take hydrogen, if you are taking hydrogen, it is +2. So again if we take plus 2, 0 to plus 2, it is oxidation. 0 to plus 2 is oxidation. 0 to plus 2, that is the hydrogen molecule oxidation number is 0. 0 to plus 2, increase in the oxidation number, so oxidation. In cupric oxide, copper oxidation number is plus 2, it is getting decreased to 0, so this is reduction. From oxygen to oxygen, no change in oxidation number. No change in oxidation number. No change in oxidation number. So this reaction therefore very clearly explains, that means in the given equation both reduction as well as oxidation is taking place parallelly. Suppose one more example I would like to give you. This is example 1. Example 2, you take zinc oxide solid plus carbon solid, you get zinc solid plus carbon monoxide gas. So here zinc is plus 2 and here zinc is 0 oxidation state. So plus 2 to 0 reduction. Carbon is 0 here, here the carbon is plus 2 oxidation state. So you can take here carbon to carbon 0 to plus 2, it is oxidation reaction. It is oxidation reaction. So this is a perfect example of the redox reaction taking place simultaneously. The reduction reaction is taking place, simultaneously reduction is taking place, and simultaneously oxidation is taking place. Here zinc in zinc oxide, zinc is getting reduced to zinc, and the carbon is getting converted to carbon monoxide. So both oxidation and reduction, both of them are involved parallelly, therefore we can call it as the redox reaction. So the next part of the discussion, that is corrosion. Corrosion is simply also called corrosion, otherwise it is also called rusting. Rusting is nothing but chemical oxidation of metal surface in the presence of moisture. So in other words, if you take a piece of iron rod, say this is a piece of iron rod which is uniform in its surface, and this is the moisture. This is moisture. Moisture contains O2 plus water. This is piece of iron piece. So during corrosion, what we notice is the metal oxide when it comes in contact with the X number of moles of water liquid plus O2 gas, immediately it forms Fe2O3 dot XH2O. Here this is light brown color. This is going to become reddish brown color. So when you say chemical oxidation, rusting also here means this is chemical oxidation. When you say chemical oxidation, iron solid plus O2 gas gives rise to Fe2O3. So here the iron, when you are passing oxygen, it is getting rusted. So whenever a metal is converted to metal oxide, it gets rusted. So here More oxidizing metals, more reducing metals, they can reduce the less reducing metals in the case of rusting. Here, rusting of iron in the presence of moisture, that is O2 plus H2O, we call it as corrosion. Rusting of iron is corrosion. Then conversion of silver, which is grey, to Ag2S, that is black. We call this process as tarnishing. In other words, that is silver, which is a solid, it reacts with sulfur, again it's a solid, it becomes Ag2S, which is black. Once the silver, which is in grey color, converts to black color, it is called tarnishing. Also, more reducing metal oxidizes and reduces metal oxide. Example, zinc plus cupric chloride. Zinc gets corroded. Zinc chloride and copper is prevented from corrosion. This is called sacrificial metal reactivity. Sacrificial metal reactivity, we call it as sacrificial metal reactivity. More reducing metal gets oxidizes and reduces less reducing metal oxide, or metal chloride, because this is a metal chloride. So this is metal chloride. Metal oxide you can take, or metal chloride you can take. Metal chloride. So the next part of the discussion is rancidity. If you go for rancidity, that is fats and oils when oxidized they turn rancid. Obnoxious smell or odor. So to prevent this obnoxious, to prevent this rancid nature of fats and oils, what we do is, for prevention of rancidity is done by adding antioxidants. Antioxidants to fats and oils. Antioxidants for fats and oils. So if you go for this antioxidants, anything which prevents the decay, that is, we can add vinegar, we can add small amount of vinegar, we can add small amount of flavoproteins and so on. All this will prevent the rancid nature of the oils and fats. So here let us solve some questions in metals and non-metals. Let us solve some questions. That is exercise in metals and non-metals. Non-metal exercise in, you can take it like this, exercise in chemical equations and calculations. And metals and non-metals. A small questionnaire we are going to do. When magnesium reacts with, first question, magnesium when reacts with air, the products obtained. The products obtained are, so the reaction is very simple. Magnesium is a solid, it reacts with air because air is a mixture. So air contains both oxygen as well as nitrogen gas. So there is a possibility for it to give both magnesium oxide plus magnesium nitride, Mg3N2, or the same reaction you can write magnesium solid plus oxygen gas gives rise to magnesium oxide solid. Balance the equation, take 2 over here, take 2 over here, and magnesium solid plus nitrogen gas gives rise to Mg3N2 solid, magnesium nitride. Balance the equation, take 3 over here, this is magnesium nitride. And this is magnesium oxide. Magnesium oxide. Again, take magnesium oxide, is a solid, you dissolve it in water, liquid, it forms a base, magnesium hydroxide, aqueous, it's a base. Again, magnesium nitride, if you take solid plus H2O, liquid gives rise to magnesium hydroxide, aqueous plus ammonia vapors. Balance the equation, take 2 nitrogens here, so assign 2 here, 3 magnesium, so assign 3 here. I think the number of oxygens are 6, so take 6 over here. The reaction is automatically balanced. So the second question is Fe2O3 solid plus aluminium solid gives rise to Al2O3 solid plus iron solid. So in this is the equation which is given to us. First one, balance the equation, mention the type of reaction, and identify species getting oxidized and reduced is the question. So first question again, if you want to answer it, so I repeat here, balance the equation. If you want to balance the equation, here only we can balance it. There are 2 irons and here we have 3 oxygens, we have only 2 aluminiums, 3 oxygens. So I think if I place 2 here, the reaction gets balanced. There are 3 oxygens, here we have 3 oxygens, okay, fine. There are 2 irons, here there is only 1 iron, so the reaction is already balanced. So that means 1 mole of ferric oxide reacts with 2 moles of aluminium to give 1 mole of aluminium oxide and 2 moles of iron. The reaction is already balanced. Mention the type of chemical reaction. This is nothing but the chemical displacement. Mention the type of chemical equation means chemical reaction means here only we can give the answer. This is chemical displacement. We can say that the reaction is chemical displacement because here the iron in ferric oxide, the iron is getting displaced in the form of iron. The ferric ion is getting displaced in the form of iron from its oxide. This is metal oxide, and this is metal. So metal is being separated from metal oxide, and here aluminium is acting as a reducing agent. Identify the species which is getting oxidized and species which is getting reduced. Identify the species which is getting oxidized and the species which is getting reduced. We can say that here the iron oxide is getting reduced. The iron oxide is getting reduced, and aluminium to aluminium oxide. So here aluminium is getting oxidized. So therefore it's a sort of redox reaction. Question number 3. Why color change occurs when iron rod dipped in copper sulphate solution? When iron rod is dipped in copper sulphate solution. So therefore what I am doing here is I am just taking a vessel wherein which here this is copper sulphate, and here we are dipping an iron rod. It's a piece of iron rod. This is brown color. Here what is happening is once iron is dipped in copper sulphate, the reaction takes place like this: iron solid plus copper sulphate aqueous. This is dark blue. It becomes ferrous sulphate aqueous plus copper, pale blue, and this is going to become greenish brown. That means here what is happening is the copper is getting reduced. In copper sulphate, copper is getting reduced, and here iron is getting oxidized. The reason because of that, you find that means the iron is trying to reduce the cupric ions in copper sulphate to copper. That is why you find that there is a change in the color. You can see that there is an intense greenish color, and here there is a dip in the copper sulphate solution to pale blue color. The reaction takes place, and once the reaction is coming, it becomes the intense greenish brown color appears. Intense greenish brown color appears, and this is how we can answer the question. So the next part of the question is, give an example of decomposition reaction involving absorption of electrical energy. So here, if you take the answer for this is, if the electrical energy is converted to chemical energy, the process we call it as electrolysis. Example, you can take water, liquid, 2 molecules of water, subject it to electrolysis. It gives 2 moles of H2 gas plus 1 mole of O2 gas. 1 mole of O2 gas. So this is electrical decomposition reaction. Here water is getting decomposed. So the 2 molecules of water or 2 moles of water is getting decomposed to give 2 moles of water is getting decomposed to give 2 moles of hydrogen gas and 1 mole of oxygen gas. Here perfectly it is utilizing the electrical energy. Electrolysis involves utilization of electrical energy. Utilization of electrical energy.